All right, let's do part 2 of lesson 5.4. I know that was, when I picked off from the last video, I was pretty sleepy, but now I'm well rested and ready to do some more. And hopefully no yawning in this one. Okay, so last time in the first part of 5.4, we covered some general strategies for, and just sort of general tips for solving quadratics in terms of applications for real-world scenarios. And we're just going to look at a few more examples. So you can look at that video to kind of see some of our previous examples, but we're just kind of continuing off that. So the first two examples I'm going to do 3 examples in this video. The first 2 are going to be over area, and then the third example is going to be over system of a quadratic and linear. So you have 2 lines meeting. Okay. So here's the first one, and this one is classic. In fact, you're going to see this problem again in calculus because maximizing area, particularly with regard to rectangles and whatnot, you're going to see that in calculus it's way easier to find than with algebra. Although I guess that's a matter of opinion. Right? It depends on how hard you think it is to take a derivative. It also depends on the type of function it is, of course. So anyway, let's work this. So example 3, maximizing area. A rectangular fence is built against the side of a house. The perimeter of the fencing is 68 feet. What is the maximum possible area of the fenced area? Okay. So the first thing, whenever you get a problem like this, you should draw a picture. That is exactly what you should do, which is what I'm going to do now. I'm going to draw a picture. Let's see if it'll make that. Oop. I would like that to be a nice house. Let us try that one last time. There we go. This is going to be my house, and I am building a fence against it. So let's switch to red here. So this fence right here, like so, that's my fence right there that is built against the side of a house. Now it says the perimeter of this fence is 68 feet. And that's the only information I'm given. That's it. All I know is that the perimeter is 68 feet. I have nothing else. It tells me nothing about the side lengths. So here's what I'm going to do. I'm going to label the side lengths a variable of my choice because I don't know what these lengths are, so they're unknowns, which means they can be represented with variables. So I'm going to call the length that is perpendicular to the house x, which means this length is x, and then I'll call the parallel fence, the piece of the fence is parallel to the house, I'll call that y. Okay? Now, this problem doesn't give you any direction on which length should be which. Sometimes it might, and it might use the same verbiage as I did, saying like, oh, call the side length of the fence that's perpendicular to the house x, which means you need to know what those words mean, right? But in this case, you kind of have free reign to choose whatever letters and put them wherever. Okay, now, all this requires, really, is that we have an understanding of what perimeter and area are. Perimeter is just the sum of the outside lengths, right? It's the length all the way around a shape. So my perimeter here, I say P, well, I know that P is 68 feet, of course, but perimeter is the sum of the lengths, so it's x, y, x, right? And notice that side length on the side of the house, that's not part of the fence, right? The house is the house. I'm using that as a side of this pen, right? So 68 feet equals 2x plus y. So that's my perimeter. Now I want to set up an equation for area because I'm trying to maximize area. Of course, area is just length times width, so my length is x, my width is y. It's going to be x times y. Okay. Now, you might notice here, this is a system. This is a system of a quadratic and linear. Isn't that interesting? Well, actually, I should say, maybe I've misspoken. It's not exactly a quadratic linear yet. Neither of these is, right? You could call the first one linear. I'm not sure about the other one, though. So here we go. let me backtrack. I'm sorry. Forget what I said there. This is just a system with x and y variables. But what's different is this isn't a linear system because I'm not adding my x's and y's in both equations, right? Area is x times y. That's not linear, right? That's something else. But we could make it into a quadratic, and here's how. Keep in mind here, I'm trying to find maximum area, which means, can I make, I'm going to write this down, can I make area a quadratic equation? And ponder about that. Yes, you can, using substitution. Use substitution. I'm going to write that down just right there. So what do I mean by that, right? Well, 68 equals 2x plus y. This implies that y equals 68 minus 2x. I get this result by subtracting 2x from both sides, right? So if y equals 68 minus 2x, then it follows that a equals xy means a equals x times 68 minus 2y. I'm sorry, minus 2x. And I have done this, I've accomplished this by using substitution. Now, if I distribute this, I get area equals negative 2x squared plus 68x. Notice I'm kind of putting that in standard form, right? Ax squared plus bx. I'm distributing x, but then I'm also simultaneously rearranging into standard form. But that's a quadratic, right? And because that's a quadratic, we can find the maximum area by finding the vertex. So I'm going to say find vertex of this quadratic. Now, I'm going to, in the last video, we talked about, I need to, let's silence those notifications. Okay, don't want family texting me right now. In the last video, I talked about you could complete the square, or you could use this negative b over 2a business, right? I'm gonna do the new method because we've done plenty of completing the square practice. So let me pick a different color here. Let's go to yellow. So I'm gonna pick yellow, and I say use x equals negative b over 2a, because that's what I want to do, is find the vertex, right? So then negative b will be a 68, so that's negative 68 over 2 times a, that's 2 times negative 2. So I just really have 68 over 4 here. 68 divided by 4. What is that? Let's say 1/16? No way. No. Hold on. Mr. Spake wants a calculator. 68 divided by 4. 17. I knew something was fishy. Oh, I guess, okay. I would have been able to find that result pretty easy. Okay, I don't know what I was doing there. Okay, that equals 17. Okay, so when x is 16, meaning when this side length right here is a side length of 17, that will produce the maximum area possible for this fence. So now I'm just going to look at my area function. Area equals negative 2x squared plus 68x. And I'm just going to use 17 to find the maximum area. Negative 2 times 17 squared plus 68 times 17. Again, this can be accomplished by completing the square, but we don't really have to do that because I want you to use this method For practice, oh, it's not 60, it's 17 squared plus 68 times 17. 578. Nice. Area equals 578 feet squared. And ta-da, that is my answer. Okay. Pretty simple. Kinda. The challenge of this problem is being creative enough to realize that this is a system of equations you can use substitution on to create a quadratic. That is new. And that's just some creativity stuff there. That's not any, you know, yeah. All right, I'm rewriting this. It follows that. I'm only doing this for my own purpose. Okay. Also, side note. I'll say note. Note the dimensions. I'm going to zoom in here. The dimensions that maximize this area. Area are 17 foot by 34 feet, where x equals 17 and y equals 34. All right. If you're not sure where I got this, okay, look, x we found was 17. That's what maximizes the area. You have two ways you can find y, and that is through resubstituting x back in. So I'm not going to do that here. I trust that you can figure that out. You found the maximum area. You know x is 17. So if area is length times width, you take the area, you divide it by 17. That gives you 34. Alternatively, you also know the perimeter adds up to 68. So double 17, take away that from 68. It's 34. You get y equals 34. But I just point this out because you might be asked to specify the dimensions. Okay. Now let's look at a border problem. All right, example 4, border. So we talked about these in the last unit, unit 4. And I know that they gave some of us some trouble. So let's go over it again. A rectangular garden is surrounded by a walk of uniform width. The dimensions of the garden are 16 by 24 feet. So let us draw the garden. And now let us draw the walk. That is not good. Let me try that one more time. Is that better? That's a little better. Is it perfect? No, but it will suffice, all right? Dimensions of the garden are 16 by 24 feet. So I know that this is 16, and I know that this is 24. And I'm going to call the width x, right? Now, the problem doesn't tell me to do that, but you could call it anything you want. We're going to call it x. So I'll call this width x, which means this width is also x because it's of uniform length. All right. And I wanted to make sure my picture was small enough so that I had room to write here. So I want to find the width of the walk. Notice here, right? I want to find the width, meaning I want to find x if I know that the area of the walk is that. So I have a few goals here, right? My goal is to find x, right? My goal is to find x. But what do I need? I need area of walk in terms of x. This is what we require, right? So how do we do this? Well, we talked about this in the previous unit, which is why we were setting up for this moment. And that is to label the other dimensions, right? So I might take my little gold here. The outside dimensions are 24. Ooh, you know what? Just because it's a picture, I should probably switch those out. This should be 16. This should be 24 since that's the longer length. Okay. So I'll call this 16 plus 2x. You see, because it has a side length of 16, then an x, and then an x, right? And then the other side length is 24 plus 2x, since it's a side length of x and a side length of x together with 24. Okay, so I'm going to call the area total is length times width, 24 plus 2x times 16 plus 2x, which if I multiply that out, let's see, 24 times 16, I don't know what that is. 24 times 16, 384. Beautiful. So I'll put that at the end here, please. 384. And then that's 4x squared. Ooh, okay, 48 plus 32. Certainly I can do that in my head, but I do not want to. 80. Okay, so plus 80x. Nice. Okay, and if you're not sure how I got the result, you can discover that for yourself by using the distributive property on that. Okay, distribute it out, be good practice for you. Okay, see if you get the same result I do. And I do not like the way that looks, so I'm going to edit it. Say plus 384. Nice. Okay, so that's the area total. Now, what's the area of the garden, right? What's the area of the garden? Area of the garden is 24 times 16, which we just discovered was 384. So, if I want the area of the walk, that equals the area total minus the area of the garden, which equals 4x squared plus 80x, plus 80x. And then it's plus 384 minus 384, but I think you can see how those cancel each other out, right? Be good independent practice for you to do. Also, the area of the walk around the garden is 255. So this is the area of the walk. So area walk equals 225, which equals that, right? So if I take this, right, if I take these two things together, then I get 4x squared plus 80x equals 225. This is a standard form equation if I rearrange it, that I can set equal to 0. Right? And now I just want to solve for x, meaning I want to figure out what value of x makes this true. So if you're solving for x, notice this is different from what we were doing in the previous problem. I'm not looking for a maximum area or anything like that. I'm just solving for x. Now, when I'm solving for x, you put it in standard form, and then you use, well, you use the variety of techniques we've learned to figure out what x is. Now, let me see. I could try factoring, right? I could try factoring. I don't want to do that, though, because that would require doing 4 times negative 225. I mean, wait, should I? Okay, look, let's just humor ourselves. What's 225 times 4? Let's just humor ourselves. 900. Shoot, that's 90 and 10, isn't it? Oh, my goodness. So we could do two methods here, right? All right, I'm going to say two methods. Factoring or quadratic formula. Formula. Let's just try that. Formula. Okay. Either way is going to work. If you do factoring, though, let's see here. I'm gonna just do factoring. It's negative 900. Negative 900. And this is 80. So look, if I do 90 times 10, I get 900. So make that 10 negative, then 90 minus 10 is 80. So this is 4x squared plus 90x minus 10x minus minus 225. So factor by grouping. Can I take 4 out of 90? No, I can take 2 out though. 2x, and I'm left with 2x plus 45. And then if I subtract, okay, I do minus, let's pull out 5 here, because I can't pull out 10. I get 2x plus 45 equals 0. So then this factors as 2x minus 5 and 2x plus 45 equals 0. So then what does x equal, right? What does x equal? Well, if I set this, I gotta zoom in here. If 2x minus 5 equals 0, then x equals add 5 over and divide by 2. X equals 5 halves. Or 2x plus 45 equals 0. Subtract 45 and divide by 2. X equals negative 45 over 2. But think about side length, right? Hold on. I want to say side length. Zoom in here. Side length can't be, can you guess what I'm going to say? Negative. So I automatically rule that result out. Therefore, right, so I'll switch back to green. Therefore, x equals 5 halves. Or you could say that x equals 2.5 feet. Okay? I mean, you could say 5 halves of a foot, but I mean, if you're going to, right, look, talk to a gardener. Are you going to tell the gardener that it's 5 halves of a foot? Or are you going to say it's 2.5 feet? They're going to want that as a decimal, right? So, there you go. Ha-ha! We did it. And that was nicely solved through factoring. You could do quadratic formula as well. I want you to notice, let's just go to Desmos because I'd like you to see it. All right, x equals negative b. What was that, 80? Because was it positive 80 or negative 80? Positive, okay, so x equals negative b plus or minus the square root of b squared minus 4a. What was a? 4. C, and C was negative 225. All over 2 times a, which was 4. Hey, look at that. It's 2.5, right? Ta-da, quadratic formula. And if you change that plus to a minus, oh, shoot, oh, gosh, it's negative, right? And we don't want negative side length. So we go with the positive result, and that satisfies our beautiful problem. Okay. Fantastic. Fantastic. So multiple approaches here, right? You could factor, you could use quadratic formula, you could even solve by completing the square if you wanted to, whatever method you like, all right? Whatever method suits your fancy, as they might say. All right, let's do the last one, because I want to be done with this video, and I want to be done with it. Not because I don't enjoy this. I enjoy this thoroughly, believe me. It's the weekend, and I would like to use my time doing some other things. I'd like to save the lesson on this wonderful mathematics for the week. Okay, so let's look at example 5. Then this is a system of a quadratic and linear, okay? A man jumps from a cliff 360 meters above the ground. During his free fall, his height above the ground is modeled by the quadratic equation. Ta-da! And a few seconds later, he releases his parachute, and his height above the ground is modeled by the linear equation. Ta-da! Right? And it says, note, x is the time after jumping, and y is the height above ground. This is a little important because we could try and visualize this as, oh, man's jumping. Okay, maybe like man jumps, and then here he pulls his parachute. And that is what's going on. True. But this axis is time, and this axis is height, right? And like I said in the last video, you want to be careful when you're working with these because what the graph will show you isn't the physical reality of what you're seeing. It's just height with respect to time. You can't see time, okay? So, okay, after how many seconds did he release his parachute? Well, we're looking for where does the quadratic, which is falling, meet the parachute? Or, yeah, which would meet the linear, which is the parachute. Because if we were to sketch this, right, what we're looking for is that point. Looking for this point. So all this is a system, okay? It's a system where y equals negative 4.9 x squared plus x plus 360, and y equals negative 4x plus 140. But I want you to know, so if we're looking for where they meet, we're just looking for when these two equations are equal, right? Because the quadratic has to have the exact same point as the linear, which means they have to meet, they have to touch, which means whatever x value, y value I choose, it has to satisfy both. Now, if you look, this is already solved in terms of y. We don't have to do any sort of fancy substitution here. We can just set them equal. Set them equal. So I get negative 4.9 x squared plus x plus 360 equals negative 4x plus 140. Now, if I just put this into standard form equation, add 4x and subtract 140, I get negative 4.9x squared plus 5x. What's 360 minus 140? Is that 220? Equals 0. Okay? Now, look, you can try factoring this if you really wanted to. Maybe it's not factorable, though. Probably not factorable because there's a decimal. Or you could try quadratic formula, right? So we'll just, because we're looking for x, right? Looking for x. And I'll just say, let's just be quick with this. Use quadratic formula. Okay? Now look, I mean, you can factor if it's factorable. You could factor, you could complete the square, but we're just going to do quadratic formula. X equals negative b, which is 5, plus or minus the square root of 5 squared is 25, minus 4 times a, which is negative 4.9, c, which is 220, all over 2 times a, which is negative 4.9. Okay. And that's just a calculator thing, right? You just punch that into a calculator. No big deal. No big deal. So let's try that. I say negative 5 plus or minus 25, or it's just 5 squared, times 4 times, is this negative 4.9 times, was it 220? All divided by 2 times negative 4.9. Okay, so I get negative 6.21. Let's just round that up. Equals negative 6.21, or if I change this to a minus, I get 7.23. So 7.23. So let me ask you, viewer, student, whoever you are watching this video, which one is it, right? Which one is it? Well, it ain't that one, right? Time, not negative. So my answer is, right, I'll say, where can I put this? You know what? Here's what I'm going to do. I'm going to take my little lasso tool. I'm going to say, hey there, time not negative. Oh, cool. You're affecting that. Let's try that one more time. Can we try that? Oh, nice. Okay, you know what? That's okay. Because there's this great thing called the erase button. I'll just say it up here. Time not negative. Therefore, I wanted to save the space here. Therefore, x equals 7.23 seconds. Done. That's it. Okay? It's pretty simple, really. It's a system of a quadratic and linear. You set them equal to each other, put it in standard form, set equal to 0, and then use any methods we've been talking about, which include the quadratic formula, and solve. Okay? Then we ask ourselves, how high above the ground is the man when he releases his parachute? Well, you can use either equation, right? Because it has the same y value. Same y value for either equation. Pick one. And substitute x equals 7.23. That's it. That's all you got to do, right? Because this is the time he releases his parachute. So if we want to figure out how high he was, we just plug the time into either of those equations because both of those model the height with regard to time. And they should meet at that time, so you can pick whichever one. Say y equals negative 4.9 times 7.23 squared plus 7.23 times plus 360. Or you can say y equals, or negative 4 times 7.23 plus 140. All right? In either of those options, we're going to get the same result. Or it should be pretty darn close, at least. So let's take this. We can go to Desmos, and I'll do both just to show you. Negative 4.9 times 7.23 squared plus, I do think this one's going to have a little bit more decimals just because those two decimals are getting squared. But, okay, 11109. So equals 111.09. And this, let's try this one. Go over here, say negative 4 times 7.23 plus 140. Hey, look at that. It's 111.08. 111.08. There's only a little bit difference because I'm squaring that decimal, which, by the way, was rounded, right? If I use the exact decimal, I'd probably get the exact same answer, but I rounded the decimal, so it's going to be a little off. So I might say a little off due to rounding. Okay? That's the only reason it's a little off. So let's just pick one, right? Y equals 11.09 feet. Okay? It's an accurate enough estimate, okay? It's a 0.01 difference. It's not a big deal. And there you go. That is the equation. That's all I had to do was plug that in. But it's an important thing to model. Make sure you know, right? Because you might say, wait, well, how do I do that? So, okay. I think that wraps up this video. That's it for 5.4. We got one last lesson to go, which is 5.5, which is over quadratic inequalities. I'll try to get that up soon. But yeah, I don't think there's anything else I'd like to say here. So if you got questions, send me an email, see me in Raider Time, ask me a question, whichever you like. Just let me know, okay? But these should set you up for success on that nice, lovely homework 5.4 that I gave you in class. So good luck, and you guys are doing great. I'll see you around.